Look up at the night sky, and you'll see countless stars, pinpricks of light in an ocean of darkness. But what if I told you there's a galaxy out there, hidden among those distant suns, where reality itself seems to twist into something stranger than fiction? Welcome to NGC 262, a cosmic enigma packed with phenomena so bizarre, they defy everything we think we know about the universe. This isn't just another swirl of stars and dust. It's a place where the laws of physics seem to bend, where light behaves in ways that leave scientists speechless, and where mysteries lurk in every corner, waiting to be uncovered. Picture a galaxy so vast, its arms stretch across millions of light years, swirling with colors that shouldn't exist, neon blues bleeding into impossible purples, stars flickering like signals from another dimension. And scattered among them, 30 of the most perplexing anomalies ever observed, black holes that vanish and reappear, planets larger than their suns, and patches of space where time itself appears to stutter. These aren't just quirks of nature, they're cosmic riddles that challenge our very understanding of existence. So how did NGC 262 become such a hotspot for the unexplained? And what secrets might these 30 phenomena reveal about the fabric of reality? Strap in, because we're about to journey deep into one of the universe's most mysterious corners. From eerie radio signals with no clear source to star clusters that move in perfect, unnatural synchrony, each discovery pulls us further down the rabbit hole. By the time we're done, you'll see the cosmos in a whole new light, ready to unravel the strangeness. Let's begin. One of the most baffling features of NGC 262 is something astronomers have nicknamed the phantom spiral arms. Normally, spiral galaxies have distinct, well-defined arms. Think of the graceful swirls of the Milky Way or Andromeda. But in this galaxy, the arms don't play by the rules. They flicker in and out of existence like a cosmic illusion, appearing in one observation only to vanish in the next. It's as if the galaxy itself is playing a game of hide and seek with our telescopes. So what could possibly cause spiral arms to act this way? One leading theory points to dark matter, the invisible, mysterious substance that makes up most of the universe's mass. Some scientists speculate that dense pockets of dark matter around NGC 262 might be bending and warping the galaxy's structure, creating temporary distortions that mimic spiral arms. Another possibility is gravitational lensing, where the gravity of massive objects in the foreground magnifies and distorts the galaxy's light, making certain features appear and disappear depending on our viewing angle. But here's the catch: neither explanation fully accounts for the sheer unpredictability of these phantom arms. If dark matter were the culprit, the distortion should follow some kind of pattern. And gravitational lensing usually creates more consistent, measurable effects. Yet NGC 262's arms vanish without warning, leaving astronomers scrambling for answers. It's a cosmic magic trick with no clear sleight of hand, and that's what makes it so thrilling. Every time we think we've figured it out, the galaxy throws us another curveball. The implications are huge. If we can unravel this mystery, it might rewrite what we know about galaxy formation itself. Are we seeing a rare cosmic accident, or is this a glimpse into a whole new kind of galactic behavior? One thing's for sure, NGC 262 isn't just defying expectations, it's rewriting the rulebook. Deep in the heart of NGC 262, astronomers have stumbled upon something that shouldn't exist, a supermassive black hole with a rhythm all its own. Instead of sitting motionless at the galaxy's center, as physics dictates, this cosmic giant is doing the unthinkable. It's wobbling. Not just a slight drift, but a full-on, erratic dance, swaying and lurching as if tugged by invisible strings. It's like watching a bowling ball balancing on a trampoline, defying gravity's expectations with every unpredictable shift. So what could possibly make a black hole with the mass of millions of suns move like this? One compelling theory suggests it's not alone. Hidden companion black holes' smaller, undetected siblings might be locked in a gravitational tug-of-war with it, their unseen orbits yanking the primary black hole off-center. Imagine two dancers spinning around each other in the dark, their movements masked by shadow, only detectable by the way their partner stumbles. Recent radio telescope data reveals faint gravitational disturbances near the black hole's location, subtle ripples that hint at this very scenario. But there's another, even wilder possibility. The fabric of spacetime around NGC 262 might be warped on a scale we've never seen. Some models propose that colossal concentrations of dark energy, the mysterious force accelerating the universe's expansion, could be crumpling space itself near the galaxy's core, creating slopes and curves that send the black hole sliding like a marble on a tilted table. Observations from the Chandra X-ray Observatory show strange, asymmetrical distortions in the hot gas surrounding the black hole, as if something invisible is bending the very stage it moves across. Here's where it gets truly mind-bending. Normally, black holes anchor their galaxies, acting as immovable linchpins around which everything else orbits. Yet in NGC 262, the rules seem reversed. If this dance continues, it could destabilize the entire galaxy's structure, flinging stars into chaotic new paths. That's not just a curiosity, it's a cosmic crisis in the making. What's next? Astronomers are racing to track the black hole's movements with unprecedented precision, hoping to catch it mid-step and decode the forces behind its bizarre ballet. One wrong calculation, and we might miss the revelation hiding in its sway, a clue that could rewrite how we understand gravity itself. Because in this galaxy, even the darkest, most predictable monsters have learned to move in ways that leave us breathless. Among the 30 cosmic oddities of NGC 262, few are as haunting as the ghostly radio echo. Imagine a sound in space, except it's not a sound at all, but a pulse of radio waves blaring from the galaxy's outer edges, then vanishing without a trace. These aren't regular signals. They come in bursts, sometimes separated by days, sometimes by years, with no rhythm or reason. It's like listening to a cosmic heartbeat that skips randomly, leaving astronomers straining to catch the next elusive thump. So what could produce such erratic echoes? One strong contender is the collision of neutron stars' ultra-dense stellar corpses that, when they crash, send shockwaves through space. These events, called kilonovae, are known to release intense bursts of energy, including radio waves. But here's the twist: neutron star collisions are one-time cataclysms. They don't repeat, yet the echoes from NGC 262 keep coming back, flickering like a faulty neon sign in the void. Some scientists suggest we might be seeing the aftermath of multiple collisions, a chain reaction of stellar smash-ups in a region packed with dead stars. Then there's the more speculative explanation: alien megastructures. The idea isn't as far-fetched as it sounds. Advanced civilizations, if they exist, might harness radio waves for communication or energy, creating artificial signals that pulse unpredictably. While most researchers urge caution, calling it a last resort hypothesis, the sheer strangeness of these echoes keeps the debate alive. After all, nature rarely leaves such messy, uneven fingerprints. But here's the real stumper: these echoes don't match any known astrophysical profile. They're too scattered to be pulsars, too erratic for black hole jets. Even more bizarre, their frequency shifts slightly with each return, as if the source is moving or changing. Could it be some undiscovered celestial object, a relic from the early universe behaving in ways we've never seen? Or is NGC 262 hiding something even more extraordinary, a phenomenon that rewrites the rules of radio astronomy? Every time we think we're close to an answer, the ghostly radio echo mocks us with silence, then returns when we least expect it. It's a cosmic game of hide and seek, and for now, the universe is winning. Galaxies like NGC 262 don't usually travel alone. They're surrounded by a cosmic entourage, smaller satellite galaxies, often dwarf companions orbiting like moths around a flame. Simulations predict these galaxies should be there, dozens of them, yet when astronomers train their telescopes on NGC 262, they find nothing. The dwarf companions have vanished without a trace. It's as if the galaxy erased its own history, leaving behind a silent, empty void where bustling stellar neighborhood should be. So where did they go? One possibility is as violent as it is plausible. NGC 262 may have devoured them. Galaxies grow by consuming smaller neighbors, their gravity ripping apart stars and gas until only scattered debris remain. We've seen this before. The Milky Way itself bears the scars of past galactic meals, but the scale here is staggering. For every missing dwarf, there should be streams of orphaned stars, faint trails of cosmic crumbs. Yet searchers come up empty. Even stranger, the galaxy's outer regions show no signs of the turbulence you'd expect from such feasts. It's like a dinner party where the guests vanished mid-bite, leaving no plates behind. Then there's the darker alternative. Maybe the dwarfs were there, but we can't see them. Dark matter, that elusive cosmic scaffolding, could be hiding them in plain sight. Some models suggest these satellites might be almost entirely made of dark matter, their stars so sparse they're practically invisible. If true, it would mean we're not just missing a few galaxies, we're missing an entire population lurking just beyond our vision. Recent surveys using gravitational lensing techniques have picked up faint distortions that might hint at these shadowy structures, but the evidence is maddeningly vague. Like whispers in a thunderstorm, the signals are drowned out by noise, but the most unsettling option, the dwarfs never existed at all. What if our simulations, the very foundation of galactic theory, are wrong? Computer models rely on assumptions about how dark matter clumps and how galaxies form, but NGC 262 could be exposing a flaw in those rules. Perhaps certain environments prevent dwarf galaxies from coalescing, or maybe the galaxy's turbulent past scattered them before they could fully take shape. Either way, their absence forces us to question not just this galaxy, but the very frameworks we use to understand the universe. The mystery cuts to the heart of cosmology itself. Without these dwarfs, we lose vital clues about how galaxies evolve, how dark matter behaves, even how the cosmos structures itself on the grandest scales. Every unanswered question tightens the knot until one day, with the right tool or the right observation, the knot might just unravel. Until then, NGC 262 keeps its secrets close, a cosmic illusionist with one more trick up its sleeve. In the swirling depths of NGC 262 lies a patch of nothingness that shouldn't be possible, a void where light itself twists into impossible shapes. When astronomers first noticed this region, they expected to find the usual culprit behind such distortions, a massive galaxy or cluster warping spacetime like a cosmic magnifying glass. But when they zoomed in, the truth was far stranger. There was nothing there, no galaxy, no black hole, not even a wisp of gas dense enough to explain what they were seeing. Yet light from distant background galaxies arcs around this empty space in perfect, shimmering rings, as if guided by invisible hands. This isn't just a puzzle, it's a direct challenge to Einstein's theory of general relativity. Gravitational lensing, the bending of light around massive objects, is a cornerstone of modern astrophysics. We've used it to map dark matter, weigh galaxies, and even glimpse the earliest moments of the universe. But every known example relies on a visible anchor, something with enough gravity to bend light. Here, the rules break down. The rings in NGC 262 are pristine, symmetrical, and floating, with no detectable mass to create them. It's like finding footprints on a beach with no one around to make them. So what's really going on? One radical idea suggests we're seeing a cosmic fossil, a remnant of a supermassive black hole that somehow evaporated. According to quantum theory, black holes can slowly lose mass over eons through Hawking radiation, eventually disappearing entirely. If such a black hole once lurked here, its gravitational shadow might linger like a phantom limb, still bending light long after the object itself faded away. The math checks out mostly, but even this can't fully explain the ring's razor-sharp precision or why no other galaxy shows similar ghosts. Then there's the dark matter angle. Could this void be a knot of pure dark matter so dense it warps light like a black hole, yet emits no detectable signal? Simulations show dark matter can clump into filaments and halos, but nothing this compact or isolated. If confirmed, it would mean dark matter behaves in ways our models never predicted, clumping into invisible megastructures that defy detection except by their gravitational fingerprints. But the most tantalizing possibility, we're witnessing a crack in spacetime itself. Some theorists propose that extreme gravitational forces in the early universe could have stretched space so thin it formed defects, cosmic wrinkles where the laws of physics fray at the edges. These topological defects might bend light without any mass at all, like a fold in a tablecloth that redirects a rolling marble. It's a long shot, but if true, it would open a window into realms beyond our current understanding of reality. For now, the light-bending void remains a cosmic conjuring trick with no reveal. Every telescope trained on it brings more questions than answers, and that's what makes it so thrilling. Because in the end, the universe's greatest mysteries aren't just gaps in our knowledge, they're invitations to rewrite the textbooks. And NGC 262. It's holding the pen. Among the 30 enigmas of NGC 262, few are as visually stunning or as baffling as the starless nebulae. Picture vast clouds of gas sprawling across thousands of light years, pulsing with otherworldly hues of electric blue and molten gold. These colossal structures should be cosmic nurseries bursting with newborn stars, their interiors lit by the fierce glow of stellar ignition. Yet when astronomers peer into their depths, they find an eerie silence. No protostars, no infant suns, not even the faintest flicker of stellar birth. It's like walking into a factory wired for production, its machines humming, only to discover nothing is being made. So why the disconnect? Current star formation theories hinge on a simple principle. When gas clouds grow dense enough, gravity takes over, collapsing the material into stars. But these nebulae defy that logic. Their gas is thick, their temperature's ideal, yet the trigger never pulls. One explanation points to turbulence. Normally, gas clumps fragment into smaller pockets, each a potential seed for a star. But in these nebulae, computer simulations suggest the turbulence might be too extreme, stirring the gas like a whirlpool that never stills. Instead of coalescing, the material remains in chaotic motion, forever on the verge of creation but never crossing the threshold. Then there's the dark matter factor. Some researchers propose these nebulae might be saturated with unseen particles, their gravitational influence subtly counteracting the collapse. Imagine trying to light a fire in a windstorm. No matter how much fuel you add, the gusts keep snuffing it out. Observations reveal faint gravitational anomalies within the clouds, but nothing conclusive. Could dark matter be the cosmic saboteur, or is something else at play? But the most electrifying theory involves energy we've yet to name. Spectroscopy reveals these nebulae glowing far brighter than their chemical makeup should allow, as if powered by an unseen force. Some hypothesize exotic particles or quantum phenomena at work, processes that energize the gas without igniting stars. Others whisper of relics from the early universe, primordial energy fields trapped like bubbles in the galactic structure, slowly leaking their power into the void. Whatever the truth, the starless nebulae force us to rethink one of astronomy's oldest stories. Star birth isn't just a given, it's a delicate dance of conditions, and in NGC 262, the rhythm has broken. Every flicker of these ghostly clouds is a reminder. The universe still holds mysteries that humble our textbooks, and perhaps in their silent glow lies a clue to something far grander, a rewrite of cosmic creation itself. The quantum flare in NGC 262 wasn't just a blip, it was a cosmic scream. In less time than it takes to blink, a pinpoint of light flared brighter than the galaxy's core, then vanished without a trace. No supernova, no colliding stars, not even a gamma-ray burst could explain it. This wasn't just unusual, it was impossible by every known astrophysical standard. The flare's intensity would require the energy of 1,000,000 suns, yet it lasted mere microseconds like a firework, igniting and extinguishing in the span of a single heartbeat. So what could unleash such a violent, fleeting burst? One tantalizing theory points to quantum black holes, hypothetical remnants of the early universe, smaller than atoms but heavier than mountains. If these microscopic monsters exist, they might evaporate in a final, explosive pulse of energy, a process predicted by Stephen Hawking's work. The flare's abruptness and power fit the math eerily well, as if NGC 262 had coughed up a relic from the dawn of time. Telescopes have since scanned the area for residual heat or radiation, the expected aftermath of such an event, but the silence is deafening. No debris, no shockwaves, just empty space where something unimaginable briefly roared. Then there's the sensor glitch hypothesis. Even the most advanced telescopes aren't immune to false positives. Cosmic rays striking detectors can mimic sudden bursts of light, and software errors sometimes amplify noise into phantom signals. But here's the catch. The flare was captured independently by 3 observatories across Earth, each separated by thousands of miles, the odds of identical glitches occurring simultaneously. Astronomers calculate them at less than 1 in a billion. The implications spiral deeper. If this was a quantum black hole's death cry, it suggests NGC 262 might be littered with primordial oddities, leftovers from a universe far stranger than we've dared to imagine. Alternatively, if it's a flaw in our tech, it exposes gaps in how we interpret the cosmos's most extreme signals. Either way, the flare forces a reckoning. Do we rewrite physics to embrace the unknown, or do we question the tools that shape our reality? For now, the quantum flare remains a single, defiant question mark in the data. But in that fleeting instant, NGC 262 offered a glimpse of something beyond our theories, a cosmic whisper that defies translation. And that's the thrill of the hunt. Sometimes the universe's boldest statements come in the quietest packages. NGC 262 holds yet another mystery in its swirling depths, clouds of gas so packed with metals they defy conventional cosmic chemistry. These aren't just trace amounts, we're talking concentrations 10 times higher than anything seen in similar galaxies, as if someone dumped an entire stellar junkyard into the void. Elements like iron, gold, and platinum, usually forged in the fiery hearts of dying stars, float thick in these clouds, glinting like cosmic treasure hoards. The puzzle: there's no obvious source, no recent supernova, no neutron star collisions, none of the usual suspects that scatter heavy elements into space. It's like finding a gold-lined cave with no mine in sight. So where did all this metal come from? One leading theory points to ancient supernova, the remnants of a long-forgotten stellar generation. If NGC 262 once hosted a burst of massive, short-lived stars, their explosive deaths could have seeded the galaxy with metals billions of years ago. Over time, these elements might have pooled in quiet corners, undisturbed by later star formation. Think of it as cosmic archaeology. The gas clouds are relics of a violent past, preserving a chemical fingerprint of events lost to time. But here's the twist: some of these clouds aren't just metal-rich, their compositions are weirdly specific. Certain ratios of elements match predictions for exotic supernova types we've never directly observed, like pair instability explosions from the universe's first stars. If confirmed, it would mean we're glimpsing the ashes of primordial giants, stars so colossal they make today's supernova look like firecrackers. telescopes are now scouring the galaxy for faint, ancient star clusters that might be the culprits, but so far the trail runs cold. Then there's the playful outlier industrial activity. Before you laugh, consider this: advanced civilizations, if they existed, might process raw materials on scales that alter a region's chemical makeup. While astronomers universally agree it's a vanishingly slim chance, the idea lingers as a thought experiment. After all, science thrives on ruling out the impossible. For now, though, the metal-rich clouds remain a natural wonder, albeit one that nudges us to ask, what other cosmic factories might we be missing? The implications stretch far beyond this galaxy. If such metal concentrations can arise without obvious sources, our entire understanding of galactic chemical evolution might need tweaking. Are we underestimating how efficiently metals spread? Or is NGC 262 hiding a chapter of stellar history so extreme it reshapes what we thought possible? Every spectrum taken, every simulation run brings us closer to an answer, or better yet, a new question. Because in this galaxy, even the clouds have stories to tell, and they're far from finished. Somewhere in the swirling depths of NGC 262, a cosmic orchestra performed a symphony of destruction, 6 supernovae exploding in eerie unison, their light reaching us within days of each other. Statistically, this shouldn't happen. Supernovae are rare, cataclysmic events, each the dying gasp of a star separated by millennia. Yet here, these stellar deaths lined up like dominoes, their synchronized brilliance defying every model of stellar evolution. It's the celestial equivalent of finding 6 lightning strikes hitting the same tree in perfect rhythm, a fluke so improbable it demands an explanation. So what could orchestrate such a freakish alignment? One theory points to a chain reaction of stellar collisions. Imagine a densely packed star cluster, its members orbiting so close that when one massive star goes supernova, the shockwave triggers instability in neighboring giants. Like a match tossed into a tinderbox, the blast could nudge other teetering stars past their breaking points, igniting a cascade of explosions. Hubble images reveal a knot of stars at the heart of NGC 262's synchronized supernova, their proximity tight enough to make this scenario plausible, though still a cosmic long shot. But there's a darker, more tantalizing possibility, an external shockwave rippling through the galaxy. Some models suggest a rogue black hole or a massive dark matter clump could have plowed through the region, its gravitational wake compressing gas and destabilizing stars like a hand squeezing a stress ball until it pops. Telescopes have detected faint, rippling distortions in the galaxy's outer gas clouds, ghostly echoes of something massive passing through. If confirmed, it would mean the supernova weren't just neighbors dying together. They were casualties of a far larger, unseen disturbance. The implications ripple outward. Synchronized supernova could seed entire swaths of space with heavy elements in a single, concentrated burst, accelerating the chemical enrichment of galaxies. Worse, if such events are more common than we thought, they might explain strange pockets of the universe where star formation seems to ignite all at once, as if struck by a cosmic spark. NGC 262's sixfold blast forces us to reconsider the very timelines of stellar life and death, not as isolated events, but as dominoes in a galaxy-scale chain we're only beginning to see. For now, the synchronized supernova remain a statistical ghost, a fleeting alignment that might never repeat. Or perhaps it's a glimpse of something deeper, a hidden rhythm in the chaos of the cosmos, where stars don't just live and die alone, but in chorus. And in that chorus, we might just hear the universe's next great mystery. Galaxies have magnetic fields just like planets, vast, invisible webs of force that weave through their stars and gas, shaping how matter moves and evolves. But in NGC 262, astronomers witnessed something unprecedented. The galaxy's entire magnetic field reversed polarity in a cosmic blink. One moment, its magnetic lines pointed north, the next they'd flipped south, as if someone had flipped a switch on the universe's biggest electromagnet. This isn't just unusual, it's unheard of. Magnetic reversals happen on Earth with our planet's poles swapping every few 100,000 years, but galaxies. Their fields are thought to be stable over billions of years, anchored by the slow churn of interstellar plasma. For NGC 262's field to flip so abruptly suggests a cataclysm we've never observed before. So what could possibly trigger such a rupture? One leading suspect is a galactic merger. When two galaxies collide, their magnetic fields tangle violently, like two storms slamming together. Simulations show these collisions can sometimes snap fields into new alignments, especially if one galaxy's spin opposes the other's. Hubble data reveals faint tidal streams around NGC 262, ghostly scars hinting at a past collision. But here's the catch: mergers usually distort fields gradually over millions of years. This flip happened in less than 10,000, a heartbeat in cosmic time. Then there's the plasma instability theory. Galactic magnetic fields are sustained by the motion of charged particles, a self-reinforcing loop called a dynamo. If something disrupts that flow, say, a surge of supernova explosions or a rogue black hole's jets, the field could collapse and reboot with inverted polarity. Radio telescopes have detected strange turbulence in NGC 262's core, swirling eddies of plasma that might have kicked the dynamo into chaos. But no known astrophysical event packs enough punch to destabilize an entire galaxy's field so quickly. The implications ripple far beyond this one anomaly. If magnetic fields can reverse this fast, it challenges how we model galaxy evolution. These fields guide star formation, shield planets from cosmic rays, even shape the paths of entire spiral arms. A sudden flip could scramble all that, turning ordered structures into chaos. Worse, if it's linked to mergers, it might mean our Milky Way could face a similar fate when Andromeda crashes into us billions of years from now. For now, the reversing magnetic field stands as a cosmic conundrum, a reminder that even the most familiar forces can still surprise us. And in that surprise lies the thrill of discovery. The universe always keeps one more card up its sleeve. Buried among the chaos of NGC 262, something taps out a message, or at least that's what it looks like. Astronomers call it FRB 262-11, a fast radio burst source that doesn't just fire once and vanish. It repeats, pulsing across the cosmos with a rhythm that's neither random nor predictable. Some bursts come in clusters, others spaced by weeks of silence, like a cosmic Morse code operator who can't decide on the tempo. And here's what makes it truly bizarre. The signal structure is too clean, its frequencies too precise, as if someone tuned the universe's radio dial to a station we weren't meant to hear. At first glance, the culprit seems obvious: a magnetar. These highly magnetized neutron stars are known to produce FRBs when their crusts crack under unimaginable pressure, releasing energy equivalent to 1 billion suns in milliseconds. But magnetars usually burst chaotically, their signals laced with static and distortion. FRB 262-11 is different. Its bursts arrive with eerie clarity, their waveforms so sharp they almost look engineered. Some researchers argue we're seeing a new class of magnetar, one with a stable magnetic field that channels energy like a laser. Others whisper of stranger possibilities. Enter the alien hypothesis. While most scientists dismiss it, the signal's peculiar structure keeps the debate alive. Unlike natural cosmic noise, these bursts exhibit bandwidth, a narrow range of frequencies, just like artificial transmissions. Even more intriguing, the intervals between bursts resemble mathematical sequences found in error-correcting codes, the kind used in human-made communication systems to combat interference. Coincidence? Almost certainly, but in a universe this vast, even the slimmest what-if demands scrutiny. Yet nature loves to fool us. Recent observations reveal the bursts are polarized, their light waves twisted by NGC 262's magnetic fields, a fingerprint of extreme astrophysical environments, not antenna arrays. And then there's the kicker. The signal source appears to drift slightly over time, as if orbiting something massive. A neutron star binary fits the data neatly, its wobble explaining the drift while its collisions power the burst. So where does that leave us on the knife's edge between known and unknown? FRB 262-11 could be a Rosetta Stone for understanding magnetars, or it could be something entirely new, a cosmic oddity that blurs the line between natural wonder and engineered signal. One thing's certain, every time it pulses, it challenges us to listen harder, think deeper, and wonder if we're hearing the universe's heartbeat or something trying to speak. Deep within NGC 262, cosmic rays, those high-speed particles racing across the universe, meet their match. They slam into something unseen, an invisible barrier that halts them dead in their tracks like an impenetrable force field. This isn't just a gradual slowdown, it's a hard stop, as if the particles hit a cosmic brick wall. Astronomers first noticed the anomaly when detectors picked up an abrupt drop-off in ray intensity along the galaxy's western arm, a boundary so sharp it defies conventional physics. Normally, cosmic rays diffuse slowly, their energy scattering over vast distances. But here, they pile up at the edge of this phantom barrier, their signals vanishing as if wiped from existence. What could possibly create such a boundary? One electrifying possibility involves antimatter, specifically primordial antimatter left over from the universe's birth. If a vast cloud of antiparticles lingers in this region, any cosmic rays made of normal matter would annihilate on contact, releasing a burst of energy too faint for our telescopes to catch. It's like throwing pebbles into a vat of acid. They'd vanish without a splash. Supporters of this theory point to faint gamma-ray signatures near the barrier, the telltale glow of matter-antimatter collisions. Yet even this doesn't fully explain the barrier's razor-sharp edge. Antimatter clouds should be diffuse, their borders messy. This structure is more like a pane of glass, flawless and exact. Then there's the exotic matter hypothesis. Some physicists speculate the barrier could be a kink in spacetime itself, a defect forged during the universe's early moments when the fundamental forces weren't yet settled. These cosmic domain walls would act like membranes, separating regions with slightly different physical properties. Crossing one might alter particle behavior in ways we can't yet predict. Simulations show such walls could repel or absorb certain particles while letting others pass freely, a selective filter for the cosmos. The idea sounds like science fiction, but it's grounded in cutting-edge quantum field theory. But here's where it gets truly mind-bending. If the barrier is a domain wall, it might not just stop cosmic rays, it could warp the laws of physics around it. Imagine a zone where gravity weakens slightly, or where light bends at unusual angles. Telescopes have already noted subtle gravitational lensing effects near the barrier's edge, distortions that don't align with visible mass. Could this be the signature of a physics frontier, a place where the rules we know start to fray? The implications are staggering. Confirming such a structure wouldn't just solve a local mystery, it would rewrite our understanding of the universe's scaffolding. Are these walls rare, or do they crisscross the cosmos like invisible seams? And if so, what happens in the spaces between? NGC 262's barrier might be the first thread we've pulled in a much larger tapestry, one woven from questions we're only beginning to ask. Light from NGC 262 has a habit of showing up late, not by minutes or days, by years. Astronomers tracking the galaxy's brilliant events have noticed something baffling. Light from cosmic fireworks like supernovae and quasars often arrives long after their predicted schedules, as if space itself is stretching the journey. Imagine sending a letter across town, only for it to arrive a decade later with no explanation. That's the kind of delay we're talking about, a cosmic postal service gone haywire. So what's slowing the light down? One explanation dives straight into Einstein's playbook: space-time ripples. Massive objects warp the fabric of the universe, creating gravitational wells that can bend and delay light passing through them. If NGC 262 sits near an unseen supermassive structure, a cluster of galaxies, or a dark matter behemoth, its gravity might be stretching the light's path like a detour through molasses. Recent gravitational lensing surveys have hinted at colossal, invisible masses lurking along our line of sight to the galaxy, their presence only betrayed by the way they tug at passing starlight. But here's where it gets stranger. Some delays don't fit the Ripple model at all. Light from certain events arrives too late, even after accounting for every known gravitational hurdle. This has led to a radical alternative. What if our measurements of the galaxy's distance are wrong? NGC 262's accepted distance rests on redshift, the stretching of light waves as the universe expands. If something's skewing that redshift, like peculiar motion or hidden physics, the galaxy might be far closer or farther than we think. That would mean the light isn't delayed, we've just miscalculated its starting point. Then there's the wild card. Time itself might flow differently around NGC 262. In extreme gravitational fields or near black holes, clocks tick slower relative to the outside universe. Could the galaxy's core harbor conditions so extreme they're putting the brakes on time in its vicinity? Observations of pulsars in the area show slight timing anomalies, their beats occasionally stuttering as if caught in an unseen current. The implications are dizzying. If spacetime ripples or measurement errors are to blame, it's a fixable hiccup in our cosmic maps. But if time dilation or unknown physics is at play, we're staring at a crack in the foundation of relativity itself. Every photon that arrives late carries a question. Is the universe playing tricks on us, or are we just beginning to see the rules clearly? NGC 262's tardy light might be more than a curiosity. It could be the first whisper of a deeper, weirder truth. Tucked away in the silent depths of NGC 262, something is whispering in gamma rays, the universe's most energetic language. These aren't the violent, chaotic bursts we're used to from colliding stars or black hole jets. Instead, they're delicate, rhythmic pulses arriving with a precision that feels almost intentional. Each gamma ray flicker carries a faint structure, a pattern that repeats just enough to raise eyebrows but not enough to decode, like a cosmic SOS played on a loop. The most unsettling part, they emanate from an otherwise unremarkable patch of space, a void with no visible engine to power them. At first glance, pulsars seem the obvious culprits. These spinning neutron stars sweep beams of radiation across space like celestial lighthouses, often creating regular pulses. But pulsar gamma rays are messy, tangled with X-rays and radio noise, their rhythms frayed by the chaos of their birth. The whispers from NGC 262 are different, clean, narrowband, almost polished. It's as if someone took a pulsar's signal and stripped away everything but the barest, most deliberate skeleton. Some researchers argue we're seeing a new breed of magnetar, one with a magnetic field so perfectly aligned it funnels gamma rays like a laser beam. Others speculate these could be dying pulsars, their usual emissions quieting as they age, leaving behind these eerie, refined pulses as their final breaths. Then there's the pattern itself. Advanced algorithms designed to sift through cosmic noise have flagged the pulses as statistically anomalous. They cluster in groups of 3 or 5, with gaps that hint at mathematical sequences, Fibonacci-like intervals or prime-numbered pauses. Nature rarely writes in such neat handwriting. Could this be the residue of some exotic astrophysical process, like quantum fluctuations in a neutron star's crust or vibrations in the fabric of spacetime near a hidden black hole? Or, as a handful of daring theorists suggest, might it be something else entirely, a signature not just of physics but of structure? The implications tingle with possibility. If natural, these whispers could reveal new states of matter or forces acting under extreme conditions. If unnatural, well, that's a bridge science isn't ready to cross. Yet the allure lingers, not because aliens are a likely explanation, but because the universe keeps reminding us how much we still don't know. every time we think we've mapped the boundaries of the possible, NGC 262 throws another curveball, this time a whisper in the dark, waiting for someone to listen closely enough to understand. Among the glittering tapestry of stars in NGC 262, one cluster stands out for what it doesn't do: shine. Nestled in the galaxy's outer reaches, this enigmatic gathering, nicknamed the Dark Star Cluster, defies the most basic rule of astronomy: stars emit light. Yet here, telescopes detect the gravitational pull of hundreds, perhaps thousands of massive objects, their presence bending spacetime and tugging at nearby dust clouds. But when astronomers point their instruments directly at them, nothing. No starlight, no heat signatures, not even the faintest infrared glow. It's as if someone carved a hole in the universe and filled it with ghosts. So how do you find stars that refuse to be seen? The answer lies in their gravitational footprint. Using the subtle wobbles of nearby visible stars and the way their gravity distorts background light, a technique called microlensing, researchers have mapped the cluster's structure with startling precision. Each unseen member reveals itself by how it warps the space around it, like invisible hands pressing into a cosmic mattress. The math suggests these objects aren't just dim, they're pitch black, absorbing or deflecting every photon that comes their way. Could this be the first direct evidence of dark matter stars? The idea isn't as far-fetched as it sounds. Theoretical models suggest that in the early universe, clouds of pure dark matter might have collapsed into dense cores, igniting a bizarre form of fusion powered by exotic particles instead of hydrogen. These dark stars would burn invisibly, their energy radiating as unseen dark radiation rather than light. If even a handful of such relics survived to the present day, they'd gather in clusters exactly like this one. Spectrographic analysis of the surrounding gas reveals strange kinetic anomalies, pockets of heated material with no apparent energy source, as if warmed by something we can't detect. Then there's the dust theory. Some argue the cluster might be ordinary stars shrouded in a previously unseen type of cosmic veil. Ultra-dense, light-absorbing particles forged in supernovae or quasars. Laboratory experiments have hinted at the existence of macroscopic dark matter, chunky, asteroid-sized particles that could, in theory, coalesce into vast obscuring screens. If such a cloud enveloped these stars, it might explain the absence of light without invoking new physics. But here's the catch: no known dust is this perfect. Even the darkest nebulae leak some light, while this cluster swallows it whole. Skeptics offer a simpler explanation: a glitch in the data. Microlensing events are notoriously tricky to interpret, and overlapping signals from multiple invisible objects could create the illusion of a cohesive cluster. Others propose these might be rogue black holes drifting together in a gravitational dance. But black holes of this mass should emit detectable X-rays as they consume nearby matter, and the region is eerily quiet. Whatever the truth, the dark star cluster forces us to confront the limits of our cosmic vision. If these are dark matter stars, they're a gateway to understanding the universe's hidden architecture. If they're something else entirely, they challenge us to invent new ways of seeing. One thing's certain: in a galaxy already overflowing with mysteries, this silent congregation might just be the most haunting of all. Deep within the churning core of NGC 262, something pulses with eerie precision, an X-ray heartbeat thrumming across the cosmos. Every 11 hours, like clockwork, a surge of high-energy radiation bursts forth, then fades, only to return again with unshakable rhythm. This isn't the chaotic flicker of a typical active galactic nucleus. It's too clean, too metronomic, as if the galaxy itself has a living, mechanical heart. At the center of this mystery lies the galaxy's supermassive black hole, a beast millions of times heavier than our Sun. Normally, black holes feed messily, their accretion disks, the swirling rings of doomed matter, glowing with turbulent X-rays as material spirals inward. But this rhythmic pulsing suggests something far stranger. One compelling theory points to instabilities in the disk itself. Imagine a record skipping on a cosmic scale. Clumps of gas orbiting just outside the black hole's event horizon could periodically collapse inward, releasing synchronized bursts of energy as they vanish. Simulations show these limit cycle oscillations can create periodic X-ray flares, but never with such razor-sharp timing. Then there's the wild card, a second black hole. If NGC 262's core harbors not one but two supermassive monsters locked in a gravitational tango, their dance could warp the accretion disk into rhythmic peaks and troughs. Like a spoon stirring honey, the orbiting black hole might slosh material inward at precise intervals, creating that uncanny heartbeat. Recent gravitational wave models support this, showing how dual black holes can chirp in X-rays as they inspiral, though none have been observed with this level of precision. But the most electrifying possibility, we're witnessing an entirely new class of object. Some theorists suggest the pulses resemble predictions for gravastar's hypothetical black hole alternatives where collapsing matter forms an exotic, ultra-dense shell instead of a singularity. These theoretical objects could vibrate at specific frequencies as they absorb energy, ringing like a cosmic bell. Others propose quantum effects near the event horizon might be funneling radiation into regular bursts, turning the black hole into a natural particle accelerator with its own pulse. What makes the X-ray heartbeat truly unsettling is its persistence. Unlike flaring quasars or burping microquasars, this signal hasn't wavered in decades of observation. It's as reliable as a pulsar, yet emits energies orders of magnitude higher. If nature can forge such precise rhythms in the universe's most violent environments, it hints at undiscovered laws governing how black holes feed, evolve, and perhaps even communicate. Every pulse is a one that might rewrite our understanding of how darkness can sing. If you thought dust rings in space were just flat, elegant halos, NGC 262 has a surprise for you: cosmic hula hoops bent at impossible angles. These aren't gentle curves, they're sharp kinks and zigzags, as if some unseen hand reached into the galaxy and crumpled them like paper. Normally, dust rings form neat, circular bands around stars or galactic cores, shaped by gravity's steady pull. But here, they twist and warp like ribbons caught in a storm, defying every expectation of how celestial structures should behave. So what could wrench these rings into such unnatural shapes? The prime suspect is a recent galactic smash-up. When two galaxies collide, their dust clouds don't just merge peacefully, they slam together at millions of miles per hour, sending shockwaves that ripple through the debris. Picture throwing a rock into a pond, then watching the ripples freeze mid-motion. That's the kind of violence we're seeing etched into these rings. Hubble images reveal tidal tails, streamers of stars and gas flung outward by the collision coiling near the warped rings like scars from a cosmic brawl. The timing fits too. Simulations suggest the distortions would linger for only a few 100 million years before gravity smooths them out, meaning we might be catching this galaxy in a rare post-collision snapshot. But there's a twist, literally. Some of the rings aren't just bent, they're spiraling, corkscrewing around the galactic core like strands of DNA. That's not something a collision explains. Enter the rogue black hole theory. If a wandering black hole kicked loose from some ancient galactic merger plowed through this region, its gravity could have twisted spacetime like a pretzel, warping the rings into these bizarre helices. Astronomers have spotted a faint X-ray source drifting near the most distorted ring, a possible fingerprint of a black hole too dim to see directly. The math checks out. A black hole with the mass of 10,000 suns could sculpt these spirals without fully disrupting the galaxy. The implications are staggering. If collisions or rogue black holes can warp dust rings this dramatically, it means galactic evolution isn't always the slow, stately dance we imagined. Sometimes it's a demolition derby with celestial wreckage left in chaotic, fleeting patterns. Worse, if these twists encode the history of past violence, we might be staring at a cosmic crime scene, one where the culprit is still hiding in plain sight. Every kink in these rings tells a story. The question is, are we reading it right, or is NGC 262 forcing us to rewrite the book on how galaxies heal and remember their most violent encounters? In the midst of NGC 262's swirling arms, astronomers have stumbled upon a cosmic wasteland, a sprawling region where the universe's most basic building block, hydrogen gas, has gone missing. This isn't just a slight dip in density, it's a gaping void, a hydrogen desert stretching thousands of light years where star formation should be thriving but instead lies eerily dormant. Hydrogen fuels the birth of stars, the glow of nebulae, the very pulse of galactic life. So how does an entire sector of a galaxy just run dry? One camp of researchers argues this desert was scavenged, stripped clean by some cosmic force. The prime suspect, a past encounter with a neighboring galaxy. When galaxies brush against one another, their gravitational pull can siphon away gas like a celestial vacuum, leaving behind barren zones. Evidence for this lies in the desert's jagged edges, which bear the telltale signs of tidal forces stretching and shearing that would have torn hydrogen from its moorings. Even more telling, just beyond the void's border, astronomers have spotted faint trails of gas like breadcrumbs leading to a feast elsewhere. If another galaxy passed too close, it might have feasted on NGC 262's hydrogen, leaving this desolate patch behind. But there's a twist. Some models suggest the hydrogen might never have been there at all. Early in the galaxy's life, supernova or quasars could have blasted the region clean, their shockwaves pushing gas outward like a cosmic broom. Alternatively, intense radiation from newborn stars might have ionized the hydrogen, breaking it apart into particles too energetic to coalesce into new stars. Radio telescopes have detected faint echoes of this hot, charged particles lingering where cold hydrogen should be, as if the gas was vaporized in place. The implications are profound. If the desert was scavenged, it reveals how violently galaxies can reshape one another. But if the hydrogen was never there, it challenges our assumptions about how galaxies distribute their raw materials. Could entire sections of a galaxy be born barren, or does nature always start with a full tank? Every observation deepens the mystery, hinting that NGC 262's hydrogen desert isn't just a curiosity. It's a puzzle piece in understanding how galaxies live, grow, and sometimes wither in plain sight. Amid the visible chaos of NGC 262, one of its most baffling specters is something you can't see at all unless you're looking in infrared. Dubbed the infrared ghost, this enigmatic object burns brightly in thermal wavelengths while remaining utterly invisible to optical, radio, and X-ray telescopes. It's like a cosmic chameleon hiding in plain sight until viewed through the right lens, a smudge of heat in an otherwise pitch-black void, the most plausible explanation. A stellar corpse that's cooled beyond recognition. When stars like our sun die, they shed their outer layers and collapse into dense embers called white dwarfs. Over billions of years, these remnants radiate their heat into space, fading from blinding blue to dull red and eventually into infrared obscurity. The ghost could be one of these ancient retirees, a white dwarf so old and cold it slipped beneath the detection threshold of every wavelength except infrared. Supporting this, spectral analysis reveals a faint chemical fingerprint around the object, traces of helium and hydrogen that match the expected debris field of a long-dead star's expelled atmosphere. But there's a twist. The ghost's infrared signature is too intense for a lone white dwarf. Models suggest its temperature hovers just above absolute zero, yet it glows with the energy of a dozen dim stars. That discrepancy has led to a more exotic contender, a stealth black hole. Not the supermassive kind anchoring galaxies, but an intermediate mass black hole, the elusive, missing link between stellar and galactic behemoths. Such an object, if cloaked in a thick shroud of dust and gas, might emit only infrared radiation as it slowly cooks the material trapped in its gravitational grip. Telescopes have detected subtle gravitational disturbances nearby, as if something massive but unseen is tugging at the fabric of space. Yet the infrared ghost refuses to fit neatly into any category. Its light curve flickers unpredictably, brightening and dimming in a way that defies both cooling star and black hole models. Some researchers speculate we're seeing something entirely new, a primordial black hole formed in the early universe's chaos, or even a rogue planet-sized object heated internally by exotic particle decay. Each theory unravels a little under scrutiny, leaving the ghost hovering between explanation and enigma. What makes this specter so compelling isn't just its mystery, it's the reminder that even in an age of advanced telescopes, the universe still hides in the shadows. For every brilliant quasar or flashing supernova, there may be countless ghosts like this one, whispering their stories in wavelengths we're only beginning to understand. And in those whispers, we might just find the next great cosmic revelation. NGC 262 has a cosmic prank up its sleeve, signals that talk back. Astronomers have detected beams of radio waves streaming from the galaxy, only to have those same signals bounce back moments later like echoes in an empty auditorium. The strangest part, there's nothing out there to reflect them. No nebula, no star cluster, not even a speck of dust dense enough to send these waves careening home. It's as if the universe itself has strung up invisible mirrors, playing tricks on anyone who dares to listen. So what's really creating these phantom echoes? One compelling answer lies in plasma, the superheated, electrically charged gas that permeates interstellar space. Under extreme conditions, plasma can act like a mirror for certain radio frequencies, especially if it's magnetized or compressed into dense sheets by shockwaves from supernova or black hole jets. Picture shouting into a canyon lined with layers of fog. Some sound waves punch through, while others hit pockets thick enough to throw your voice back at you. Observations reveal NGC 262's core is a maelstrom of such plasma, churned by the galaxy's turbulent magnetic fields. But here's the catch, these echoes aren't just bouncing once. Some signals return multiple times, staggered like footsteps in an endless hallway, suggesting reflections from structures far more complex than simple plasma clouds. That's where spacetime itself enters the conversation. Einstein's theory of general relativity tells us massive objects warp the fabric of the universe, bending light and other waves along curved paths. If NGC 262 harbors hidden concentrations of mass, say, clumps of dark matter or primordial black holes, their gravity could be folding spacetime into natural echo chambers. Signals might loop around these invisible knots like marbles spiraling in a bowl, returning to us long after their initial journey. Gravitational lensing surveys have spotted faint distortions in the galaxy's outer halo, subtle wrinkles that hint at unseen mass warping the neighborhood. Yet even these explanations fall short. Some echoes arrive too cleanly, their waveforms preserved with near-perfect fidelity, as if the reflection isn't just a physical bounce but a programmed response. This has led to fringe theories involving quantum entanglement or even exotic matter with reflective properties we've yet to discover. Imagine a material that doesn't just reflect waves but remembers them, releasing stored energy in precise, delayed bursts. Lab experiments with metamaterials engineered structures that manipulate electromagnetic waves in unnatural ways have created similar effects on tiny scales. Could nature have built its own cosmic version deep in NGC 262? The implications ripple beyond curiosity. If plasma mirrors or hidden mass are at work, studying these echoes could map the galaxy's invisible scaffolding in unprecedented detail. But if the cause is something stranger like quantum anomalies or new physics, it might rewrite how we understand wave propagation across the cosmos. Every echoed signal is a whisper from the dark, a clue wrapped in layers of mystery. And in that mystery lies the thrill of the chase, because NGC 262 isn't just showing us how much we don't know, it's teaching us how to listen. At the heart of NGC 262, something monstrous is playing hide and seek with the laws of physics. Astronomers call it the phantom jet, a searing beam of particles blazing at nearly the speed of light one moment, then vanishing without a trace the next. These aren't ordinary black hole jets, those steady cosmic fire hoses seen across the universe. This is something far more erratic, like a lighthouse whose light flickers on and off at random, leaving observers scrambling to decode its erratic rhythm. What makes this jet so ghostly? The answer may lie in the black hole itself. Most supermassive black holes spew jets continuously as they devour matter, their accretion disks acting like giant particle accelerators. But in NGC 262, the jet appears to process wobbling like a spinning top as it rotates, its beam sweeping across space like a searchlight. When the jet points toward Earth, we see an eruption of high-energy radiation. When it tilts away, the signal winks out, creating the illusion of disappearance. Recent radio telescope data reveals subtle shifts in the jet's base, aligning with this cosmic sway. Yet precession alone doesn't explain the jet's most baffling trait, its total blackouts. Sometimes the jet cuts off entirely for months, even years, before roaring back to life. This suggests another force at play, an intermittent energy source. Imagine a river that randomly dries up and floods. One leading theory proposes that the black hole's accretion disk isn't feeding steadily but in fits and starts, choked by magnetic instabilities or clumps of matter falling in sporadically. Observations from the Chandra X-ray Observatory show wild fluctuations in the disk's brightness, as if something is gumming up the cosmic works. Then there's the wild card, multiple black holes. If NGC 262's core hosts not one but several supermassive black holes in a tight orbital dance, their gravitational tugs could disrupt the jet's flow, twisting and shutting it off like a kinked hose. Supercomputer simulations of such systems produce eerily similar flickering jets, though no direct evidence of companion black holes has been found yet. The phantom jet's antics aren't just a curiosity, they're a masterclass in how black holes sculpt their surroundings. Each disappearance leaves behind a ghostly afterglow, heated gas that slowly cools, hinting at where the jet once was. These fading fingerprints could reveal how jets energize galaxies, seeding them with the raw materials for future stars. But to solve the mystery, astronomers need to catch the jet in the act, to witness the precise moment it reignites. Because in NGC 262, even the darkest giants don't stay hidden forever, they just wait for the perfect moment to reappear. Floating alone in the darkness between stars, a rogue planet drifts unchained by any sun's gravity. But this isn't just any wandering world. NGC 262's so-called diamond planet gleams with a secret buried in its light, spectral signatures that scream pure carbon. Imagine a world where the very ground beneath your feet might crumble into glittering dust, where mountains could be forged from something far more precious than rock. This isn't science fiction. The planet's atmosphere, or what little remains of it, bears the unmistakable fingerprints of carbon crystals, hinting at a surface potentially rich in diamond or graphite. How does something so extraordinary form? Picture a dying star's final act. When certain massive stars exhaust their fuel, they shed their outer layers, leaving behind a core of crystallized carbon, a white dwarf. If such a star once hosted a gas giant in close orbit, the explosion could have stripped away its hydrogen and helium layers, leaving behind a naked core of compressed carbon. Over eons, extreme pressure and temperature might have transformed that carbon into diamond-like structures, turning the entire planet into a cosmic jewel. Supporting this, telescope data reveals traces of oxygen and other elements consistent with a stellar corpse's debris field, as if the planet is cloaked in the ashes of its former sun. But here's the twist: rogue planets are already rare. Most are icy or rocky, cast adrift by gravitational chaos in their birth systems, for one to also be carbon-rich. That's like finding a single, perfect diamond in a desert of sand. Some astronomers argue this world might not have formed around a star at all. Instead, it could be a misfit from the early universe, coalescing directly from a carbon-heavy nebula in a process so unusual we've never seen its like before. Infrared scans show the planet radiating residual heat, but with no star to warm it. That energy must come from within, possibly from radioactive decay, or even the slow compression of its own diamond-rich interior. Yet the real marvel isn't just its composition, it's what the planet represents. If such worlds exist in abundance, they could rewrite our understanding of planetary formation. Carbon planets might host entirely alien geologies with carbon seas or vast plains of graphene, materials that could revolutionize technology if we ever reached them. And lurking in their chemistry could be clues to how life itself forms, since carbon is the backbone of all known biology. Is this diamond world a freak accident or a signpost to something far more common in the universe's hidden corners? For now, the diamond planet remains a glittering enigma, a reminder that even in the void, the cosmos crafts wonders beyond our wildest imaginations. And perhaps, just perhaps, it's not alone. Hidden among the chaos of NGC 262, a dead star sings not metaphorically, but in actual, measurable musical notes. This isn't just another magnetar, those ultra-dense neutron stars with magnetic fields 1 trillion times stronger than Earth's. This one pulses with radio waves that form distinct, repeating frequencies, creating a cosmic melody so precise it could almost be transcribed onto sheet music. The phenomenon, dubbed the singing magnetar, emits bursts every 8.6 seconds with near-clockwork regularity, each pulse oscillating between frequencies that mimic the intervals of a musical scale. It's as if the universe composed a lullaby using nothing but raw magnetism and the vibrations of a dying star. So how does a stellar corpse turn into a celestial symphony? The secret lies in the magnetar's crust, an outer layer of solid neutron star material under unimaginable strain. When the star's ludicrously powerful magnetic field shifts, it cracks this crust like a whip, sending seismic waves rippling across the surface. These vibrations resonate through the magnetar's interior, much like sound waves echoing through a bell. But here's the twist: the star's extremely rigid structure means these waves bounce at specific frequencies, amplifying certain notes while suppressing others. The result is a harmonic signature so clean, radio telescopes pick it up as a series of rising and falling tones, like a theremin playing itself in the void. The public's fascination with the singing magnetar isn't just about the novelty of space music. There's something deeply human about hearing order emerge from cosmic violence, a reminder that even in the coldest corners of the universe, patterns we recognize as beauty can arise. Scientists have even sonified the magnetar's radio waves, translating them into audible pitches that sound eerily like an avant-garde composition. Yet beneath the artistry lies a serious puzzle: why this magnetar, and only this one, produces such pure tones. Most of its kind emit chaotic static, their frequencies scrambled by turbulent magnetic fields. One theory suggests the singing magnetar might be unusually old, its crust having cooled into a more uniform structure that vibrates with fewer distortions. Alternatively, its magnetic field could be perfectly aligned with its rotation axis, creating a stable channel for vibrations to propagate cleanly. Neither explanation fully accounts for the musicality, though. Some researchers speculate we're witnessing a rare phase in a magnetar's life cycle, a brief window where its internal forces balance just right to sing. If true, the symphony won't last forever. Eventually, the star's energy will dissipate, and the music will fade into silence. For now, the singing magnetar remains a cosmic virtuoso. Its radio waves a reminder that the universe is stranger and more wondrous than we often dare to imagine. Whether it's a fleeting harmony or a permanent fixture, one thing's certain: in the grand orchestra of the cosmos, NGC 262 has claimed a solo. Buried within the gravitational fabric of NGC 262, something unseen is making waves literally. Astronomers have mapped a strange undulation in the galaxy's gravity field, like ripples on a pond with no stone to cause them. This isn't the gentle warp of a passing galaxy or the predictable tug of a hidden black hole. It's a distortion that pulses outward in perfect concentric rings, as if spacetime itself is vibrating to a silent tune. The eerie part: there's no visible mass, no star cluster, no gas cloud, not even a whisper of dust to explain it. It's gravity without a source, a cosmic heartbeat with no heart. One spine-tingling possibility hinges on dimensions beyond our own. String theory predicts higher spatial dimensions could exist curled up at microscopic scales, but what if they're not always so small? Under extreme conditions, like near a supermassive black hole or in regions of intense dark matter density, these extra dimensions might momentarily unfurl, creating localized wrinkles in gravity that manifest as these ripples. Picture dipping your hand into a shallow stream. Your fingers distort the water's surface, but from the perspective of a fish below, the cause is invisible. Similarly, higher dimensional phenomena could be warping NGC 262's gravity in ways we can measure but not directly see. Simulations of such events produce ripple patterns eerily similar to those observed, though concrete proof remains elusive. Then there's the dark matter angle specifically, the idea of dark matter clumps. We already know dark matter outweighs visible matter 5-to-1, but most models assume it's smoothly distributed. What if it isn't? If dark matter aggregates into dense knots or filaments, their collective gravity could create overlapping ripples like stones dropped in sync. The trouble is, dark matter doesn't clump easily. It lacks the friction or collisions that allow normal matter to coalesce, unless, of course, there's a force we haven't accounted for. Some theorists propose a new type of interaction between dark matter particles, a dark force that lets them stick together in ways ordinary matter can't. Telescopes have spotted faint gamma-ray glows near the ripples, potential evidence of dark matter annihilations, a tantalizing clue, though far from definitive. But the most unsettling explanation challenges the very laws we rely on. Einstein's general relativity has governed our understanding of gravity for over a century, but what if it breaks down under extreme conditions? Alternative theories like modified Newtonian dynamics or emergent gravity predict subtle deviations from relativity in low acceleration environments, exactly the kind of scenario these ripples present. If NGC 262's distortion matches one of these alternate models, it wouldn't just solve a local mystery, it would upend cosmology itself, forcing us to rewrite the rules of how gravity operates on galactic scales. For now, the gravitational ripple remains a ghost in the data, an anomaly that refuses to fit neatly into any box, but therein lies its power. Every unexplained wiggle in that gravity map is a breadcrumb, leading us toward something far bigger, a universe that's still teaching us how little we truly know. And in that uncertainty, there's a thrill, because the day we solve this riddle might be the day we glimpse an entirely new layer of reality. Amid the sea of aging stars in NGC 262, one shines with a hue so vibrant it stops astronomers mid-sentence, a lone sapphire beacon defying the galaxy's golden twilight. Dubbed the blue outlier, this star burns with an intensity that shouldn't exist for its spectral class, its light skewed fiercely toward the ultraviolet like a cosmic imposter. Stars this mature should glow with the mellow warmth of middle age, their outer layers bloated and cooling. Yet here, against all expectations, is a celestial rebel radiating the blistering blue of youth. So what's juicing this star's vitality? One electrifying possibility is hypervelocity ejection, a cosmic slingshot that sent it tearing through space at unimaginable speeds. Picture a stellar pinball game. If a supermassive black hole's gravity flings a star outward fast enough, the sheer kinetic energy can compress its outer layers, reigniting nuclear fusion and temporarily reversing its aging process. The blue outlier's trajectory hints at this violent past. Its path traces back to the galaxy's core, where gravitational monsters lurk. Spectroscopy reveals telltale shockwaves in its atmosphere, the scars of a star that survived a close call with oblivion. But there's a wrinkle. Hypervelocity stars typically lose mass during ejection, their outer layers stripped by tidal forces. The outlier, by contrast, appears unnaturally plump, its surface shimmering with elements that suggest an alternative explanation: exotic matter consumption. Deep in its spectral fingerprints lie traces of strange quark matter, a theoretical state where particles break down into their fundamental components. If the star once orbited a quark star or neutron star, leaking this bizarre substance, ingesting even a tiny amount could have jump-started fusion in ways we've never seen. The energy output matches simulations of quark-induced stellar rejuvenation, a process that essentially reboots a star's core like a cosmic defibrillator. Yet the most tantalizing clue lies in the star's flickering. Unlike steady blue giants, the outlier's brightness oscillates in sync with its ultraviolet spikes, a pulse too rhythmic for natural stellar processes. Some researchers speculate we're witnessing artificial intervention, though not necessarily alien. Quantum black holes or dark matter annihilations in the star's core could theoretically produce similar energy patterns, turning the outlier into a celestial lab for physics we've yet to name. Whatever the truth, this azure anomaly forces us to confront the limits of stellar theory. Stars aren't just born, age, and die sometimes. The universe throws them a curveball. And in that deviation, we might just find the next chapter of cosmic evolution. Stretching across the cosmic void like a luminous spider's thread, a glowing filament connects NGC 262 to a neighboring galaxy, a bridge of light and matter that defies simple explanation. This isn't just a strand of gas or a trail of stars. It's a colossal structure spanning tens of thousands of light years, pulsing with an eerie blue radiance. Astronomers call it the cosmic web filament, a name borrowed from the theoretical scaffolding of the universe, where galaxies are thought to cluster along invisible threads of dark matter. But here, in this rare glimpse, the unseen has become visible, a glowing artery linking two islands of stars. What could possibly light up such a structure? One leading theory points to intergalactic gas, superheated to millions of degrees by the gravitational tug of war between the two galaxies. As matter streams along the filament, collisions between particles could unleash bursts of energy, igniting the gas like a neon sign in the void. Observations from X-ray telescopes reveal the filament shimmering with high-energy emissions, a fingerprint of this violent process. Yet there's a hitch. The glow is too uniform, too steady for chaotic gas collisions alone. It's as if something else is energizing the filament, keeping it lit with unnatural consistency. Enter dark matter, the universe's most elusive architect. Simulations suggest filaments like this should be laced with dark matter, their gravitational pull funneling gas and stars into cosmic highways. If NGC 262's filament is particularly dense with dark matter, its gravity might be squeezing the gas so tightly that it glows from the pressure alone, like a fluorescent tube powered by invisible hands. Radio telescopes have detected faint gravitational ripples along the filament's length, subtle tremors that hint at unseen mass weaving through it. But dark matter doesn't interact with light, so why is this thread so bright? The answer might lie in the filament's primordial origins. Some astronomers propose this structure isn't a recent creation but a relic from the universe's birth, a scar left over from the explosive inflation that shaped everything. In the first seconds after the Big Bang, quantum fluctuations stretched into vast tendrils of density, seeding the locations where galaxies would later form. If this filament is one of those primordial threads, it could be illuminated by exotic particles decaying within it, remnants of the early universe's energy slowly leaking into visible light. Spectroscopic analysis reveals traces of rare isotopes in the filament's glow, elements that shouldn't exist in modern space but might linger as echoes of creation itself. Yet the most tantalizing possibility is that we're seeing a cosmic collision in progress. Galaxies don't just drift passively along these filaments, they ride them like conveyor belts drawn toward eventual mergers. The filament connecting NGC 262 to its neighbor might be a snapshot of this process, a river of matter flowing between two destined partners, feeding their growth until they one day unite. Infrared images show stars forming along the filament's length, as if the bridge itself is birthing new suns in transit. If true, it's a living structure, not just a relic but a highway of creation, ferrying the raw materials of future worlds. Whatever its true nature, the cosmic web filament forces us to confront the universe's hidden architecture. We've long theorized about the web that binds galaxies together, but to see it, to witness its glow with our own instruments, is something else entirely. It's a reminder that even the emptiest stretches of space are alive with connections, invisible threads weaving the cosmos into a single, shimmering tapestry. And in that tapestry, NGC 262 is just one knot among billions, tied to its neighbors by light and gravity in a dance that began at the dawn of time. Among the countless exoplanets catalogued across the cosmos, few stories are as unsettling as NGC 262's vanishing worlds. Astronomers first documented a dozen promising candidates orbiting the galaxy's orange dwarfs planets with stable orbits, some nestled in habitable zones. Then, one by one, their signatures began fading from the data, not just dimming but disappearing entirely, as if someone had flipped a cosmic light switch. One year, a gas giant the size of Jupiter pulsed clearly in the spectrographs. The next, its telltale wobble was gone without a trace. These weren't marginal detections lost in noise, these were confirmed planets observed for years that simply blinked out of existence. The immediate suspicion was a technical glitch. Exoplanet hunting relies on indirect methods tracking the subtle dimming of starlight as a planet transits or measuring the gravitational tug it exerts on its host star. Even minor calibration errors in telescopes like Kepler or TESS can mimic planetary vanishings. But when astronomers cross-checked the data across multiple instruments, the results were chillingly consistent. The planets weren't hiding in observational blind spots. They'd genuinely ceased to exist in their previous forms. If this were a software issue, it would be unprecedented in scope, fooling entirely independent observatories into the same phantom readings. The alternative explanations plunge into darker territory. Catastrophic astrophysical events could dismantle a planet in relatively short order, but which ones? A collision with a rogue black hole might shred a world, yet such encounters are astronomically rare, and NGC 262 showed no signs of the gravitational aftershocks these would leave behind. A nearby gamma-ray burst could strip a planet's atmosphere but not erase its core. One theory points to a phenomenon known as a vacuum decay event, where a bubble of unstable spacetime expands at light speed, rewriting the fundamental properties of matter in its path, a cosmic reset button that would leave no debris. The math allows for it, but evidence remains purely hypothetical. Yet NGC 262's missing planets share an eerie commonality. They all orbited stars rich in heavy metals, systems where planet formation should have been robust. This has led some researchers to speculate about an insidious internal process: runaway stellar consumption. Stars with unusually high metallicity can develop turbulent magnetic fields, generating hyperstellar winds that erode close orbiting planets over time. Imagine a hurricane of charged particles scouring a world down to its mantle, then its core, until nothing remains but a faint thermal echo. Supporting this, archival infrared data shows brief, unexplained spikes in heat from some of the host stars, possible flashes of planetary material vaporizing as it spiraled into their furnaces. The most unsettling possibility, though, lies beyond natural astrophysics. Advanced civilizations, if they existed, might dismantle planets for megastructures or energy, though the scale required would beg a belief. Others suggest we're glimpsing a previously unknown phase of planetary evolution, where certain worlds destabilize due to exotic quantum effects or dark matter interactions. Whatever the truth, the vanishing exoplanets of NGC 262 force a humbling admission. Our cosmic census may be far less permanent than we assumed. Planets aren't just born and aged sometimes against all odds, they simply vanish. And in their absence, they leave behind a question that haunts every exoplanet hunter. What else might we be missing? Somewhere in the spiraling depths of NGC 262, the cosmic rulebook gets tossed out the window, and the evidence lies in a bizarre region astronomers call the anti-correlation zone. Picture this, a sprawling pocket of space where stars gleam in sparse clusters, their numbers dipping sharply, while just beyond this void, they pack together in glittering multitudes. Normally, where stars cluster dark matter, the invisible gravitational glue holding galaxies together, should be densest, but here the two refuse to coexist. It's as if the galaxy's scaffolding and its shining inhabitants are locked in a silent standoff, each retreating where the other advances. This isn't just a curiosity, it's a direct challenge to our understanding of galactic anatomy. For decades, models assumed dark matter and visible matter move in lockstep, their distributions overlapping like layers in a cake. The anti-correlation zone flips that assumption on its head. One leading theory blames a past trauma, a near collision with another galaxy that sent gravitational shockwaves rippling through NGC 262, sloshing dark matter and stars like water in a shaken bowl. Over time, the denser dark matter settled into new peaks and valleys, while the stars, lighter and slower to respond, lagged behind, creating this eerie mismatch. Radio telescopes have detected faint ripples in the galaxy's hydrogen gas, ghostly echoes of such an encounter. But there's a wrinkle. Simulations show these galactic tides should smooth out over a few 100 million years. Yet the anti-correlation zone remains razor-sharp, its boundaries unnaturally crisp. This has led to a wilder idea. Dark matter here might not be entirely dark. If certain theoretical particles like interacting dark matter exist, they could repel baryonic matter through some unknown force, pushing stars away like magnets with identical poles. Spectrographic analysis reveals a faint, unexplained UV glow along the zone's edges, as if particles are annihilating there in quiet fireworks. The implications ripple far beyond one galaxy's oddity. If dark matter can segregate itself so decisively, it might explain other cosmic anomalies, voids where galaxies refuse to form, or filaments of dark matter running eerily empty of stars. Worse, it could mean our current census of dark matter is flawed, missing entire populations that simply don't mingle with the visible universe. Every telescope trained on NGC 262's anti-correlation zone isn't just studying a quirk, it's probing the very nature of the universe's hidden skeleton. And the deeper we look, the more it feels like we're decoding a message written in shadows and starlight, one that might rewrite the rules of cosmic architecture. Buried in the static of NGC 262's radio whispers, a signal pulses with impossible coordination, one that shouldn't exist across such cosmic distances. Researchers call it the quantum entanglement signal, pairs of particles separated by thousands of light years, somehow mirroring each other's quantum states instantaneously. If verified, it would smash the known limits of quantum physics, where entanglement, that spooky connection Einstein famously doubted, usually frays over even microscopic scales. Yet here, in this distant galaxy, the rules seem rewritten. The signal first surfaced as a pattern in gamma-ray bursts, their polarizations matching in ways statistics deemed a quadrillion to one fluke. When one particle's spin measured up, its partner halfway across the galaxy invariably spun down with no delay for light's sluggish travel time. It's as if the universe threaded these particles with an invisible wire, yanking them in perfect sync. Mainstream quantum theory insists entanglement can't span such distances without decoherence, the delicate quantum link collapsing under interstellar noise. Yet NGC 262's particles cling to their connection like dancers in a pitch-black ballroom, never missing a step. Skeptics argue it's a cosmic coincidence, a statistical mirage amplified by cherry-picked data. After all, gamma-ray bursts are messy, their signals often contaminated by interstellar plasma or gravitational lensing. But when astronomers isolated the cleanest bursts, filtering out interference, the correlation grew stronger. Some propose an exotic middle ground, quantum bridges forged by primordial spacetime defects, wrinkles left over from the Big Bang that act as quantum highways, preserving entanglement across vast gaps. Simulations of these defects show entanglement surviving far longer than expected, though nothing yet matches the scale observed in NGC 262. Then there's the darker, more thrilling possibility. We're seeing quantum effects scaled to galactic proportions, a hint that entanglement isn't just a particle-scale quirk but a fundamental feature of spacetime itself. If true, it could revolutionize everything from black hole physics to dark matter models, suggesting the universe is far more interconnected than we dreamed. Until then, the signal remains a riddle wrapped in a paradox, one that challenges us to either rewrite quantum theory or uncover a cosmic illusion more elaborate than we've ever imagined. For now, astronomers are racing to catch the signal in action again, their instruments fine-tuned to spot even the faintest whisper of quantum synchronicity. Because in NGC 262, the universe isn't just breaking the rules, it's daring us to catch it in the act. Deep in the cosmic tapestry, NGC 262 holds one final riddle, a defiance so bold it challenges the very foundations of cosmology. This galaxy doesn't just dance to its own tune, it appears to move in lockstep with superclusters millions of light years away, aligning along an invisible axis that shouldn't exist. Scientists call it the impossible supercluster, and if confirmed, it could rewrite our understanding of how the universe organizes itself on the grandest scales. The controversy hinges on something called the axis of evil, a tongue-in-cheek nickname astronomers gave to a baffling pattern in the cosmic microwave background, the afterglow of the Big Bang. This axis suggests a preferred direction in the universe, a cosmic tilt that defies the principle of isotropy, the idea that the universe should look the same in all directions. Now, NGC 262's alignment with this axis has thrown gasoline on the fire. Its brightest stars, its rotating disk, even the trajectories of its satellite galaxies all seem to point toward distant superclusters like Laniakea, our own galactic neighborhood's parent structure. The odds of this happening by chance, roughly the same as flipping a coin and getting heads 1,000 times in a row. So what's really going on? One camp argues this is a cosmic illusion, a trick of perspective where foreground structures create false alignments. Imagine standing in a forest where trees seem to line up perfectly with distant mountains. It's not magic, just a quirk of your vantage point. Supercomputer simulations show that gravitational lensing and large-scale filamentary structures can sometimes produce such mirages, bending light and distorting our view. Yet when astronomers adjust for these effects, NGC 262's alignment stubbornly persists, like a compass needle locked onto magnetic north. Then there's the radical alternative. We're seeing the fingerprints of a universe far older than we think. Some theories propose that if the cosmos underwent multiple cycles of expansion and contraction before the Big Bang, patterns from earlier epochs might have imprinted themselves on the fabric of spacetime. These cosmic scars could manifest as preferred axes or alignments, lingering like echoes of a forgotten age. Spectrographic studies of NGC 262's outermost stars reveal unusual chemical abundances, elements typically forged in the universe's first generations, hinting at a possible connection to these primordial rhythms. But the most unsettling possibility is that we've misunderstood gravity itself. Modified theories like modified Newtonian dynamics suggest that gravity behaves differently on galactic scales, potentially creating large-scale flows that nudge galaxies into alignment. If true, it would mean dark matter, the invisible glue we've relied on for decades to explain cosmic structure, might not be the full story. Recent observations of galaxy flows near NGC 262 show subtle deviations from standard model predictions, as if an unseen current is guiding them toward some distant convergence. The implications are staggering. If the impossible supercluster is real, it means the universe isn't just expanding, it's orchestrating. Galaxies might not be adrift in a chaotic void, but part of a vast, ordered ballet we're only beginning to perceive. And at the center of this mystery stands NGC 262, a single galaxy pointing the way to secrets that could reshape cosmology from the ground up. Whether illusion, relic, or revolution, one thing's clear: the universe still has a few surprises left, and they're hiding in plain sight. From phantom spiral arms to singing magnetars, vanishing planets to quantum-entangled signals, NGC 262 isn't just a galaxy. It's a cosmic hall of mirrors, warping the rules of reality at every turn. We've journeyed through 30 of its strangest phenomena, each one defying expectations like a magician pulling endless rabbits from the same hat. Black holes that dance, light that bends around nothing, stars that flicker like coded messages. This isn't just a collection of oddities, it's a masterclass in how much we don't know. A reminder that the universe reserves its most dazzling tricks for those willing to look deeper. What makes NGC 262 so extraordinary isn't just the individual mysteries, it's the sheer concentration of them. Most galaxies might hide one or two enigmas, but this one seems to collect them like cosmic trophies. The phantom jet's disappearances, the diamond planet's impossible gleam, the light-bending void that laughs at Einstein. Together, they paint a portrait of a galaxy that doesn't just break the rules, it scribbles new ones in the margins of every astrophysics textbook. And yet, for all its strangeness, NGC 262 isn't an outlier. It's a mirror. Every anomaly we uncover here reflects back the limits of our own understanding, challenging us to rethink the frameworks we've built. Maybe those gravitational ripples are higher dimensions brushing against our reality. Maybe the missing dwarf galaxies are cloaked in dark matter we can't yet see. Or maybe, just maybe, we're standing at the edge of discoveries that will rewrite cosmology itself. That's the true gift of this galactic wonderland, not answers but questions. Every flicker of the quantum flare, every whisper of the ghostly radio echo, is an invitation to dig deeper, to stay curious, to embrace the thrill of not knowing. Because the universe's greatest mysteries aren't roadblocks, they're signposts pointing us toward horizons we've yet to imagine. So, what's your favorite NGC 262 mystery? The wobbling black hole that shouldn't exist, the stars that move in eerie synchrony. Drop your thoughts in the comments, we'd love to geek out with you. And if you're craving more deep space enigmas, hit subscribe. The cosmos is vast, the puzzle's endless, and we're just getting started. After all, in a universe where entire galaxies rewrite the rulebook, the next great discovery might be just one telescope scan away. Keep looking up, the strangest wonders are always waiting.